Hello and welcome to this SimTech engineering video on Spillway simulation with CradleCFD, in particular making use of the software scFlow from Hexagon. So what is Spillway CFD simulation? Well, as you can see in this video, we have a typical spillway or chute design, comparing a smooth chute on the left with one with obstacles on the right. And the reason we would want to do something like this is to compare the velocity profiles of different chute designs for water flow exiting a dam or a stormwater drainage system. And the goal with such a simulation is to try and minimize the velocities of the water flow as it exits the chute into the riverbed system. This is well documented in literature that baffle or block chute designs are used to slow down the flow rate of water exiting a dam or a stormwater drainage system so as to minimize the amount of soil erosion that would take place in the riverbed. Why would we want to do simulations of this? Well, it's important to see that the erosion rate, the soil erosion rate in the riverbed is loosely defined as a function of the velocity squared. And so by reducing the velocity, in this case by almost a factor of 2, from 8 meters per second down to 4 meters per second, it has a significant impact on the erosion rate, the soil erosion rate in the riverbed. Obviously, with a structure like this, it's a large concrete structure. It's manufactured at great cost. It's built over an extended time period. And so you want to make sure that your design sufficiently restricts the flow to get the velocities down to the required levels, while at the same time not over-restricting the flow in such a way that it causes blockage or upstream problems because of those restrictions. And so this is where simulation can save you a lot of time and money, making sure that you get the design right. So for the rest of our video, we're going to be taking a look at how to build a model like this using CradleCFD, particularly using scFlow. And so I just want to talk you through the basics of the user interface, and then we'll jump right in and take a look at it. The first part of the user interface is the graphics window. This is where you can visually see your 3D model that you've imported, your mesh that you've created, your loads and your boundary conditions. This is where you would interact with the model graphically in the graphics window. The next most important part of the user interface is the navigation window on the left. This really is a kind of a step-by-step process for setting up your CFD model, and I'll talk you through that in a minute. And as you go through the steps on the left, you'll be creating different entities which will appear next in what's called the part tree. The part tree will list for you your fluid region, your geometry, your mesh, any surfaces that you've created for boundary conditions, for example, and other items that are created. If you select any item in the part tree, its properties appear below that in the property window, where you can either see what the properties are and in some cases change the properties directly in the property window. The last part of the graphics user interface that is important is the message window at the bottom. This is updating you with various pieces of information as you go through the process. For example, as the mesher is busy meshing the geometry, you'll be updated in the message window. You're also sometimes given prompts there with regards to what the software is expecting. Now, just before we move on to the actual creating the model, I just want to show you one more important concept which might be new to you if you are new to CFD, and that is that CFD has two parts to every model. If you're coming from a finite element background perspective, you would be most familiar with the structural aspect of creating a 3D model. And if this was a finite element model, you'd create certain loads and boundary conditions, and you would view the stresses in the structure. With CFD, however, we are interested in the fluid domain, which is this region above the structure, the region where the air and the water will flow down this chute. And so we need to create a solid model of the fluid domain. And that can be done quite simply in various CAD packages, but it is also done for us quite automatically inside of scFlow. And so this is the region that we are going to be interested in. The 3D model of the actual concrete blocks in this case really simply provide the boundaries or the flow boundaries to our fluid domain. There are cases, however, where you may want to include, as in this picture, both the fluid domain and the solid region, and that is if you were, for example, interested in solving for the temperatures in this concrete region as well, then it could be included in the computational model as well. So with that said, let's move over to Cradle and take a look at how to build this simulation model together. Right. So we firstly need to launch scFlow preprocessor from the Cradle Kicker or the Cradle toolbar. And so we do that by just clicking on this first icon here that says Launch Preprocessor. And the first step when the preprocessor launches is to give our project a name. Because it's a new project, we're going to call this one a Spillway demo. We have the option to create a folder under our working folder. In my case, I'm already in the Spillway demo folder, so I don't need to create another subfolder. Let's just correct the spelling there, demo, and we create the project. All right, so we can then minimize the kicker. And as I mentioned earlier, the navigation window on the left really is a kind of a guide that steps you through the process of creating your CFD model. And you just need to work from top to bottom. So we're going to start with prepare parts. And the first option there is parts control, which gives you functions that allow you to specify if certain parts in your model will be rotating or translating. We are not going to be using that feature in this simulation, so we can simply ignore that, and we can go directly to importing our part file. You will see that I have a model here in a parasolid format, which I'll be importing, but we can also import from various CAD packages directly into scFlow preprocessor. So there you see I've imported the structural model of my spillway, of my block chute. And as I mentioned to you, this is the mechanical model or the structural model that forms the flow boundaries. But we need to create another region for the actual solving of the water flow down the chute. And so we have a very nice tool here next in line called Create Parts. And this lets me create cubes, cylinders, spheres, or rectangles. And in this case, we're going to create a cuboid called fluid. And I can specify that it must automatically calculate the size from the selected part. So I simply select my block chute, press the calculate button. And before I create it, I can press preview. And there I can see that it's created a cube that perfectly envelops the solid model of the chute. I have an option to extend the surroundings as well. If I wanted this fluid domain to be slightly larger, that's typically used if you were looking at an external aerodynamic simulation of a car or an aeroplane. You can obviously import the CAD model of the car and then create a volume that extends beyond the dimensions. We don't need to do that in this case. And then I have an option to automatically register this new region as a fluid. And so that's a very helpful tick box to select in this case. All right, so now in my tree, you will see that I have the fluid region, and underneath the fluid region, I have the block chute. This is important because Cradle will always subtract the items lower down on the tree from the solid model, which is the highest level on the tree. So we always want the fluid domain to be at the top, and then any solid geometry that we want to subtract from the fluid domain must be below that on the tree. All right, so we've done the next step of creating the fluid domain. If our CAD model needed some cleanup, there's some very powerful tools here that you can make use of for data cleaning of the CAD model, editing solids, editing sheets, generating cross sections, transforming, rotating, scaling geometry. So if you don't have access to a CAD package, or you'd like to make use of these tools with inside of Cradle, and there's a whole suite of them available to you. We don't need to do any of that in this case. So the next step is then to build the analysis model. And here it tells us that if there are any overlapping parts, the lower parts will be subtracted or used to generate the fluid region. So what this is now doing is it's converting our solid models into a format that Cradle can use for the rest of the computational setup process. And what you will see now is that we have the fluid region at the top. We can bring it back and we have the block at the bottom, and you'll see that it's automatically subtracted the chute from the fluid region. So our fluid region now is exactly the region that we are going to need to mesh to create this solution. All right, so the next step is to create our materials. And so we're going to click on Part Material, and we're going to select our fluid region, which is this air region at the top, and we're going to assign it a fluid property. We're going to select air, that it is filled with air in its entirety from the beginning of the simulation, and then water will start to flow in, and we'll specify that in a little bit. Regarding the block chute, which is this concrete region at the bottom, we're not interested in defining it as solid and going and selecting concrete. We could, if we really were interested in solving, for example, the temperatures. But in this case, we simply say it's an obstacle. In other words, it won't be calculated from a structural perspective. It'll simply be an obstacle to the flow. All right, so we've now defined our material properties. The next step, I'm going to just switch off the concrete because we're not really interested in that going forward. The next step is to create what we call regions. Now, regions are necessary for defining boundary conditions, and it's helpful to give them logical names, and you'll see just now why that is important. So I'm going to start by creating an inlet region, and I'm going to select this face over here, and I say register. So I now have, if I double click it, an inlet region where we're going to specify our water flow coming in. The next region, if I just deselect that, deselect all faces, the next region is going to be the outlet. So in the same way, I just go through the steps of selecting that and registering the region. The third region I'm going to just call atmosphere, and that's where we are going to specify this face and the top face and this face as simply boundaries to the atmosphere. And then the last area, or second last area, is going to be these side walls. So let's create another region called walls, and I'm going to select that region and those two little ledges, not that, over there. And I'm going to select this side and that one and that one. All right, so there we've got the walls of the model as another region. And then finally, I'm going to call it the floor. Now, for the floor, we obviously need to select this face and we need to select that face, but we also need to select all these blocks as well. And so just a way to do that quite easily is to just view the model from the side, and we use this button here called the rubber box, and I'm simply going to drag a rubber box around this region. I'm going to go all the way to there, and I'm going to say mark. And what you'll see now that's done is it's selected all the surfaces inside the window as ready for application here to this region called the floor. So you can see I've got all the faces correctly selected. So I register that region. All right, so we've now created all the surface regions that we're going to need later on for assigning our various boundary conditions to the model. Okay, so we are now ready to actually go and do the setup of the CFD simulation. And so we click on this conditions box, and this conditions wizard again just steps you through the process from the top to the bottom. Not everything is required with each simulation, and you'll see that there are many options that we don't need to touch, but I'll just take you through the basics. So obviously for this simulation, we're interested in the flow. So we tick the flow box over here, and the method setting just allows you to specify certain advanced parameters, whether it's laminar or turbulent flow. In this case, we're going to just select the defaults. But in this case, we also need to select one other, which is called free surface. Right, so we're going to select the free surface as well. And what you'll see is as I select the free surface, an extra free surface menu appears here, which we'll get to just now. If I untick it, it disappears. If I tick it, you'll see it appears. So what's very nice is the wizard tries to keep things as simple as possible and only exposes that which is relevant to the choices that you've made over here. Next, we're going to click on the basic settings, and here we decide whether it's a steady state analysis or a transient analysis. Because we are solving for water flow down a chute, it certainly needs to be a transient analysis. We can specify that we want to solve at a time step of 0.001 seconds. So that's going to basically be 1,000 computations per second to accurately track the movement and the flow and the turbulence of the water as it flows down the block chute. And so because we're solving at 0.001 of a second, we're going to need 10,000 time steps to give us a total run time or a total simulation time of 10 seconds worth of flow. In this case as well, we need to consider gravity because the flow is obviously driven by gravity. And so we specify the direction. There you can see is the Z is up. So the direction of gravity is -1 and the magnitude is 9.8. Next is initial conditions. In this case, we don't have any initial conditions. We're starting with an empty domain, and the water is going to slowly flow through the domain, so we can just leave initial conditions blank. Now we move on to boundary conditions, and there's really two sets of boundary conditions that are important to us, flow and walls. We're going to start with the flow, and here you'll see the surface regions that I created earlier, and this is why it's so important to name them in a helpful way. So I can select the inlet region, and I can say I want to create an inflow condition. And so I'm going to call this Q inlet, and I want to specify a mass flow rate on the inlet of 3,000 kilograms per second. And that is going to be flowing in normal to the boundary. So here's my inlet surface on this side, and this surface is going to have an inlet of 3,000 kilograms per second of water. I can also specify here that only water will be coming in. So the liquid fraction is 1, which means 3,000 kilograms per second will be spread evenly over this entire surface as the inflow boundary condition to my model. So I set that. Then we want to move across to the outlet, which is this surface over here. And if I just select it so you can see which one I'm talking about. So that's the outlet. So I pick on my outlet over here now, and I create a pressure boundary condition. And I'm going to select an outflow pressure. This just helps the solver to know that material will only be flowing out of that surface and not potentially back in as well. So I'm going to call that P outflow, and its gauge pressure is 0. It now wants to know, well, what's going to flow out, air or water? And I don't know what the fraction of water or air on the outflow is going to be. So I simply change this option here to natural, which says to the solver, basically, you must determine what mix of air and liquid is allowed to flow out or will be flowing out as a result of the solution. And then the atmosphere, which I see I spelled atmosphere, but that's fine, are these faces over here, this one, and this one. And that's simply a pressure boundary condition, a static pressure condition of 0. So I'm just going to call this P atmosphere, and it's simply a pressure of 0. All right, so those are the flow boundary conditions that are required for this model: an inlet, an outlet, and then these sort of natural atmospheric walls which are open to the surrounding air. If I just go back to this one, I needed to also specify here that it's only gas that can enter or exit these walls. That helps the solver not to track liquid flow on those boundaries as well. Okay, so we now move on to the walls, and we could go and specify this wall. I want to create a no-slip condition on these side walls and specify what the roughness should be, and then I can do the same for the floor and give it a different roughness value. But a convenient feature is that any undefined wall where we haven't specified a boundary condition will automatically be given a no-slip condition. So in this case, we've defined all the flow boundary conditions. So everything else will automatically be given a no-slip wall boundary condition. So really, we don't actually have to do anything more. It's been done for us. We're not worrying about symmetry. We don't have any periodic boundary conditions, so we can move through that. We don't have any heat sources or radiation sources. We don't have any other fixed conditions that we need to worry about. But next is the free surface. And we've told it that we want to track the free surface between the water and the air. And so we need to specify what is the gas region and what is the liquid material. And so we specify that the whole fluid region is initially filled with air. And the liquid material that will be flowing in, we can select from our database is water. And that's all. The rest are advanced properties. If you're interested in boiling or condensation or cavitation or things like that, you can specify those properties if required. Lastly, under analysis control, this is all the solver settings, and Cradle is a very robust solver, and most of the defaults are suitable for the typical engineering problems that we would solve. The only thing I want to change in this case is under matrix solvers, I want to specify that I want it to be an accuracy-based solution, or to bias the solver towards accuracy and stability. And that's important because we want to accurately track the free surface in a transient simulation. And so we need to select that to just help us get a more accurate solution in this case. And then with regards to the outputs, this is just telling us what kind of output results we want. Because we're running a transient simulation, we're not interested in only the last cycle output. We want actually every specified cycle, and we're solving effectively 1,000 time steps per second. And so we're going to ask for outputs every 100 output steps. So basically every 0.1 of a second, we're going to get an output, and we also want the initial field to be output as well. So that's it. The rest we can leave, and we are ready to do the final step in the process then is the meshing. And so we just work our way down. We've done all the conditions. We now click on the octree meshing parameter. Now there are different ways to create the initial octree mesh, which is basically an overlapping pure hexagonal mesh. We can specify our target number of elements, and it will calculate the size based on that, or we can go into a bit of the details. I'm going to click on the detail here just to show you some of the options. And I'm going to start off by restricting the maximum octant size to around about 0.04, up to 0.4. And I'm going to just create a mesh to show you what that generates. So there you can see that it's effectively meshing the whole fluid domain with perfect hex elements of the size of 0.4 of a meter. And for the purpose of this demo, I'm going to go with that because we want the solver to run quite fast. But if you were really looking for more accurate results, you would want this to be a bit finer. So we're happy with that initial octant size, but we certainly want the mesh to be finer along the boundaries of the model. And so we click on the region settings, and here we can say, for example, right on the walls, I want to make the size 0.2, and you have to change the size in factors of 2 or half of the base size. So the base size is a hex of 0.4, so I can halve it each time I want to refine the mesh. So I'm going to say the walls must have a mesh of 0.2 with an influence range of 2. So that means 2 elements from the wall into the domain will have this size applied. But the floor, which contains all my blocks, that's where I really want the flow to be more accurate. I'm going to make the size 0.1, and I want the influence range to even be 3 elements there, and I say apply. I can also say that the inlet, I'd like the inlet and the outlet to also have a slight refinement of 0.2. So this lets you specify mesh refinement sizes for the different regions in the model. And so now if we create the mesh, you'll see that we now have the mesh very nicely refined along the outlet, the walls. You can see a size of 0.2, but the actual floor line and the blocks themselves have a mesh refinement down to 0.1. So this will be the base octree mesh that will then be used now to actually generate the final mesh. So when you're happy with the levels of refinement like this, you can say OK and OK. And then we move on to creating the actual CFD mesh. And I'm going to just accept the defaults here and say create mesh. What this will do now is it will start to prepare the geometry, generate surface meshes, then it's going to generate polyhedral meshes, and then the last step will be to create the boundary layer elements along all of the walls. And so I'm going to just let this run. I'm going to pause the video and we'll come back towards the end. It's now busy inserting the prism layers. So effectively what it does now is it finds the elements along the walls or the boundaries of the mesh, and it extrudes. You can see this in the background here. It extrudes 2 layers of elements with a thickness coefficient of 0.2 from all the walls into the middle. And this is what is known in CFD as the boundary layer mesh. And obviously for different types of simulations, you need more or less boundary layer elements to accurately capture various physics in the boundary layer. For a model like this, with a free surface model like this, 2 elements in the boundary layer is sufficient for our purposes. All right, and so there the mesh is complete, and what you will see is that it's basically created just short of 100,000 elements. You'll see if I zoom in, we have a nice refined mesh along the wall, the floor, a bit more refined along the walls, and then moving sort of to a coarser mesh in this region of the air where we're not too worried about the solving accuracy. This, I would think, is a bit coarse for our purposes, but for the sake of a demo, just to make it run faster, we would be happy with that. Also, if I zoom in here to the corners, you'll see the boundary layer very nicely, the extruded boundary layer mesh along the walls. If you want to understand what the mesh looks like inside, there's a very nice tool. We simply just, I'm going to hit X here on the keyboard, go to this rubber band box, draw a window around the mesh, and I tell it to hide all the elements inside this rubber box, and I say OK. And there we can very nicely see what the mesh looks like inside. So we've got a pure hex mesh for the majority of the domain, transitioning to polyhedral elements as it transitions towards the boundary, with the polyhedral prism elements forming the boundary layer. All right, so we have our mesh completed. Also, you'll see we've created the different entities now in the tree. So if I want to actually see my octree, I can switch it on and off here. I can switch it off in the tree. Similarly, with the actual mesh, I can switch it on and off, or the geometry, I can switch it on or off over there. So everything's available to you in the tree just by selecting these various toggles. And here we can just say show all, and we get the entire mesh back. So at this point, we're going to save the model. It's always just good practice to save when you've finished. And the last step in the navigation window on the left is to execute the solver. And so we're going to press on execute. We're going to tell it to save the files, to save the project, and to execute the solver. If I say OK, it tells me what it's going to do. And then lastly, it says, do you want me to automatically close the preprocessor for you when the solver is launched? I'm going to switch that off. If you have limited resources on your laptop or your PC, you can switch that on so that it automatically closes the preprocessor for you. Right, so now the Cradle Solver Monitor automatically launches and starts the simulation. You can see here that it starts in cycle 1. It's going to end in cycle 10,000. We're already on cycle 17. And once you've given it a few minutes to start running, it'll start to predict how long it estimates the run to be with the given mesh size and the parameters. So we can see that it's going to take roughly 2 hours or just less than 2 hours to complete. Here you can see various solver errors, and obviously if these are all nice and low, e to the minus 8, that's a good sign. If they start to rocket to e to the minus 1, 2 or higher, then your solution has gone unstable. That's a bad sign, but as long as they're all low like this and smooth, that's a good indication that the solver is progressing well. Also here, if you just roll the mouse wheel or scroll, you can track different properties in the solution. So you can see how the velocity is progressing in the simulation. You can track what the pressure is doing, the turbulence energy, dissipation of the turbulence energy, as well as the mass flux. Now, you will recall that we specified 3,000 kilograms per second coming in. So that's correct. Going out at the moment is a very low number, because basically as the water is coming in at 3,000 kilograms per second, it's pushing air out, and air's mass is very low, so this value is currently low. As the water progresses through the simulation, at some point we would expect this outlet to start going negative significantly as the mass flow of water starts to move out. Until the solution is stabilized, this green line should then eventually end up at minus 3,000 kilograms per second. So our inlet and our outlet will be balanced. All right, now while the solution is running, we can actually open the post-processor and start to monitor the results while the simulation is running, which is a very nice feature. And all we do to do that is we simply select launch the post-processor. If I click on this, it's going to tell me, do I want to open the monitor? And I say yes. And that will now open up the post-processor. So the simulation has finished. The solve is complete. So we can now go back to our kicker and we can launch the post-processor. The post-processor window will appear, and then we can minimize the kicker. And the first thing we need to do is to open the result file. So we just go to open here, and you will see that we have the result files here. I actually extended the run up to 20 seconds. So it goes all the way up to 20,000 time steps. I'm going to open the last one. That's always helpful to see where the simulation ended. And you'll see that the model comes in without any results loaded at this stage. If we look at the post-processing window, and we can't do a full demonstration at this point of the post-processor, you'll see that it does create a surface and a plane, which if we switch off, I'm going to just switch on the surface. So there's our fluid domain. And most importantly for a free surface run is what we need to see is an isosurface of the actual volume fraction of the liquid. So we're going to create an isosurface. We're going to select the variable to be the liquid volume fraction, and we're going to make it half. So what that means is if an element is more than or half full with water, we want to create an isosurface. And so there we can immediately see that everything, this is the line or the surface of an element that is half filled with water. And that looks pretty good. It looks pretty realistic. And now we can do a few more things to kind of improve what we are seeing here. For example, we can select the mesh and we can say that we want it to look like water. And so there we get a kind of a more interesting looking transparent water surface, which is nice for movies. But if we really want engineering data, we're going to switch water off. And we're going to go to transparent, switch that off as well. And let's go to contour and say on this water surface, we want to view the velocity magnitude. And so there we can see now the velocity of the water. Now this is scaled automatically to the maximum velocity anywhere in the domain. So that even includes the air, which we're not interested in. So we're going to just go to the color bar and make the maximum, let's say 10 meters per second, and have a look at what that does. We can even bring it down to maybe 5. And there we can see very nicely how the velocity of the water has dissipated as it gets disturbed on the way down. Just to show you a bit more about the post-processing, at any point, if you like what you're seeing on the screen and you don't want to have to go through all the steps to create it, you can save what's called a status file. So you would go and say File, Save Current Status, and give it a name. I've already created a status based on various aspects of the post-processing that I like. So I'm going to actually just open that status file in this case. I'm going to open my status file, and it's going to recreate the various objects that I wanted for viewing the results. So you can see that I've got my original surface, I've got an ISO surface of the water, and I've got another surface which I'm using to basically create a trim for my ISO surfaces so that I can actually visualize it as a volume. So that's just one example of how you can quickly get back to the results. If I now select my ISO surface and I want to see the velocities on that, I can simply say display velocities, and I get a nice image of the velocities with the mesh and whatever else that I want to see in the results. If I want to go back to a different point in time, I simply click up here, scroll up to the time frame that I want and select 4.7 seconds, and we should see that updating. There we go. So there we can see that's 2.9 seconds. Let's go to 4.4 seconds and 5.9 seconds. And so you can see how the flow is progressing. If you would like to create an animation of this, it obviously takes quite a bit of time to load each of the frames and to turn it into an animation, but simply to just show you where to go, you go here to camera, you select that you want to create an MP4, that's the video you want to create, you give it a name, you tell it that you want to start creating the video, and then you would play the animation down here through the toolbar, and when it's finished, you press end, and that'll automatically create an MP4 video. A screenshot will be taken of each time step and it will be strung together into a video. The post processor is very powerful, a lot of capability there. We'll need to make that another video at a later stage. Just to end off then, let me just show you a couple of the animations that have come out of this simulation. So here we can see just the flow with the velocities on the ISO surfaces. If we go to the next slide, we will see sort of a more of a transparent water representation playing a little bit slower. So you can actually see how the free surface is accurately being tracked in the Cradle solver. Let's play that again. And then finally, we can see a video of the mesh. This is a slightly more refined mesh, just to show you the results on a slightly more refined mesh running for the full 20 seconds. Also showing the velocities on the ISO surface. So you can see how the flow accelerates, and then as it hits the obstacles, it decelerates, and the block shoot is doing its job. So I think overall, very successful simulation. So hope you found that helpful and interesting. If there's anything more you'd like to know about this and how to go about creating these models for yourself, please don't hesitate to reach out to us at SimTech Engineering.